number 1 of chapter 4 is solving exponential equations. So what we're actually going to do in this unit is we're going to continue our investigation of exponential and logarithmic functions, but we're going to actually apply this to real life situations where logs and exponents are used to solve problems. Okay? When we're dealing with logs, we look at logarithmic scales such as the pH scale, the decibel scale, and the Richter scale are all considered a logarithmic scale. So if we review from the last chapter, solving exponential equations with a common base. So if I have an equation 4 to the power of x equals 2 to the power of x plus 3, can I find a common base for my 2 and my 4?
Squared.
2 squared. So I can rewrite 4 as 2 squared to the power of x equals 2x to the power, 2 to the power of x plus 3. So if the bases are the same, I can let the exponents be equal to each other. So I would multiply this out to give me a 2x equals x plus 3. So how would I continue solving this? Move the x to the other side, and what would so I'd be left with a 3 on the right hand side. What would I get on the left hand side? X. And I can double check this. I can look at what is 4 to the power of 3, which is 64, and then 2 to the power of 3 plus 3, or 2 to the power of 6, also gives me 64. So now if we look at B, I have 27 to the power of 2x minus 1 equals 9 times 3 to the power of 2x minus 1. What would my common base be? 3. Everything I'm going to rewrite into powers of 3. So 27 becomes 3 cubed to the power of 2x minus 1. What does 9 become? 3 squared times 3 to the power of 2x minus 1. So now that I have bases all the same, I can now concentrate strictly on the exponents. So for this first one, I'm going to multiply 3 by 2x minus 1, and what will I be left with? And then on the other side, if the bases are the same, and I'm multiplying the powers, what do I do to the exponents? Add them. So I'm going to get 2, and I'm going to add it to 2x minus 1. So what would you want to do at this step? Minus 1, so I've got 2x plus 1 now, and 6x minus 3. Now what?
And subtract the 2x.
Subtract 2x on each side, so I've got 4x minus 3 equals 1.
And add 3.
Add 3. So 4x equals 4.
And divide by 4. And x equals 1.
X equals 1. And again, if I was to double check that, I get 2 minus 1 is 1, or sorry, 2 times 1 is 2. Minus 1 is 1. 27 to the power of 1 is 27. And then again, I get 1 to the power of 1 over here. So 3 to the power of 1 is 3 times 9 is 27. So now if we go to 2 to the power of x equals 50, what happens if we try to use the above method to solve this question? There's no common base. I cannot easily go 2 to the power of this equals 50. So it says, determine by considering powers of 2 the two integers between which the solution must lie. So if I think of 2 squared is 4, 2 to the power of 3 is 8, what two powers would be on either side of 50? So 2 to the power of 5, which is 32, 2 to the power of 6, which equals 64. So the solution has to lie between 5 and 6. Can I get that a little bit closer to the nearest tenth? So how could I do that? How could I find to the nearest tenth what my closest solution would be?
Guess and check.
Okay, and what are you guessing and checking right now, Rachel?
Well, I started at 2 to the power of 5.5.
Okay, and what did you get?
45.25.
Okay.
And then I did 2 to the power of 5.6.
Okay.
And I got 48.50.
Okay.
And then I did 2 to the power of 5.7. And then I got 51.98.
Okay. So between these two numbers, which one's closer to 50, the 48.5 or the 51.98?
The 48.5.
The 48.5. So there's my solution to the nearest 10. Okay. But that's not an exact solution. That's an approximated solution. And if I wanted to get to the nearest hundredth, then I would have to go through the same process again. So it would be quite tedious, which means there should be another way that I can find this. And what we can do is we can use the idea of logarithms. So what I can do is I can take this equation, 2 to the power of x equals 50, and I can take the logs of each side of them. So if I take the log of each side, I get log 2 to the power of x equals log 50. My rule, my power rule, said that if I can take this power of x and bring it out in front. And I get x times log 2 equals log 50. And then to get x by itself, I would divide. Log 50 divided by log 2. And then I could use my calculator to approximate that. So if I was to approximate that, what do I get? 5.64. So to the nearest 10? I'm still getting 5.6. There's another way that I could do this as well. With my 2 to the power of x equals 50, I could start off by rewriting it as a logarithm. Log base 2 of 50 is equal to x. And then from here, to put it into my calculator, I could use my change of base. That says I take log of the argument and divide it by the log of the base. And I still get the same thing that I got before. Okay. Taking the log of each side tends to create a system that works no matter what the equation looks like. Whereas trying to write it from exponential to logarithmic is not always feasible depending on the type of expression I'm given. Okay? So class example number 1, we look at solving the following equations, expressing the solution as an exact value and to 3 decimal places. So if I look at A, I have 4 to the power of x equals 12. Always ask yourself, can you use a common base? So can I express 12 as 4 to the power of something? No. And if I look at 4, what base should come to mind with 4?
2.
2. So I should look at a base of 2. Can I write 12 as 2 to the power of something? No. So I eliminate the use of common bases, and now I can go into the method of taking the log. If this is written as a simple exponent, let's put this into logarithmic form just as it is. Log base 4 of 12 equals x. And then how would I put that into the calculator?
Log 12 divided by log 4.
Right. And to 3 decimal places, what would that equal?
1.792.
Good. Okay, so let's move on to B. I have a to the power of x plus 4 equals 40. So what should I do first? Move the 4 to the other side, and then what do I get?
8x equals 36.
Okay? Then what should I do?
Make them the same base.
Okay, can I make them the same base?
You can use 2. Can you?
2 to the power of what equals 36?
Okay, no.
No, I can get to 32, but I can't get to 36. Okay, so if I can't use common bases, now what?
You could do like turn it into logarithm.
Okay, so write it as a log, and what do I get?
Log base.
Log 8 to the power of 36 equals x.
So log base 8 of 36 log base 8 of 36 equals x. And then how would I put it into the calculator?
Log 36 divided by log 8.
And what would that equal?
1.72.
723?
Yeah.
Okay. Okay. Now when we get to C, is C written the same way as the other two? Or what's the difference between C and the other two questions?
You have an exponent on both sides.
I have an exponent in both sides. So I cannot just convert this into logarithmic form because it's going to be a mess. So this is the scenario where if I can't use a common base, I take the log of each side. Log 6 to the power of 3x equals log 3 to the power of 2x minus 1. And what does the power law tell me I can do with these exponents?
Bring them out in front.
Bring them out front. So now I have 3x times log 6 equals 2x minus 1 times log 3. So now what would I do? I have some brackets. What would I do if I have brackets?
Get rid of them.
How do I get rid of them?
Expand it out somehow.
Expand it out. So take the 2x and multiply it by log 3. 2x log 3. Take the negative 1 and multiply it by the log 3. And I get negative log 3. What am I trying to figure out? What am I trying to determine?
Value of x.
I'm trying to find x. So what do I need to do in order to find x?
Put it on one side.
Put all the x's to one side. So we need to move that 2x log 3 to the other side. How do I get rid of a 2x log 3?
Subtract it to us.
Subtract it. Okay? Now these two terms that I have on this side, Are they the exact same term? In other words, are the logs the same? Is log 6 the same as log 3? No. So I can't subtract them. I can't look at this and write down x log 3 or x log 2. I'm not even sure what combination. So what I'm going to do in this case, what do they have in common? What's the one thing that's in both terms?
The x's.
The x's. It's a common factor. Factor it out and tell me what you get. If I factor an x out of the first term, what does that leave me with?
3 log 6.
3 log 6 minus
2 log 3.
and then how would I get x by itself?
Oh, divide by the 3 log 6 on both, like
Okay.
the thing brackets on both sides.
So negative log 3 over 3 log 6 minus 2 log 3. Now we need to do some simplifying because the question actually asks me to write it in the form of log something over log something. And that's not really what I have here. I have a lot of extra logs in place. So the top, this negative, think of it as a negative 1 times log 3. So I can put it back and make this log 3 to the power of negative 1. What can I do with the 3 and the 2 on the bottom? Not subtract them. Where can I put the 3? I can put them into the power. So log 6 to the power of 3 minus log 3 squared. How can I combine these? What's my law that I can use to combine? Look on the cover of your workbook. You've got a formula sheet. It's on the front cover or the back. Look at your laws of logarithms and see which one has to do with subtraction.
You can divide.
The quotient law. So the quotient law tells me that I can divide 6 to the power of 3 divided by 3 to the power of 2. So then I can use the calculator to help me simplify. What is 6 cubed divided by 3 squared? Okay. And on the top, if I didn't want to have this negative 1 as an exponent, how could I change that? How could I change 3 to the power of negative 1 to make it a positive exponent? What's my power law? So look at this right here. How do I write this with a positive exponent, a
This is
positive
the
1?
reciprocal, so 1/3 to the power.
1/3. So I can rewrite this as log 1/3. And then I have it in the form that the question asked for, which is a positive log divided by a positive log. And now I can figure out what that equals to 3 decimal places. And what do I get?
-0.346.
Yeah. Okay. A lot of steps. A lot of the steps are algebraic steps. This right here is an algebraic step. Expanding, multiplying. Bringing the x's to the other side. Factoring out an x. So don't let the log itself start to impact, I can't do this question. Because if you want, what you could do at this step is let's get rid of the 6 and the 3 for a couple of minutes. And I could write this as 3 log times b equals 2x minus 1 times log a. Or sorry, not log a, just times a. So I make the letters different from each other because the logs aren't the same. You don't have to do this, but I'm showing you that algebraically it would still work. Because here I would get 2xa minus a, and then 3xb. Bring the x to the side. And then from here, what's my common, what do both terms have in common is an x. 3b minus 2a equals negative a, and then I can still bring this to the other side. And then I can replace that log b, or that b with log 6, and that a with log 3. So don't let the log be your limiting factor on this question, because a lot of the question is algebra, and then when I get to this point here, it's now using those laws of logs, which are given to you on a formula sheet. So it's going back and referring to that formula sheet. Okay. Question D. Is this a simple exponent or a simple exponential equation? Or is it more complex?
Complex,
What makes it complex?
probably. You have that exponent on both sides here.
I have an exponent on both sides, plus I have this, where I'm multiplying by the 2. And unlike the question above it, where I subtracted 4 on each side, I can't divide by 2 on each side. It's not going to really help. Okay? So if I don't have a simple exponent or exponential equation, then I start off by taking the log of each side. So take a look. So if I look at my logarithm formulas, my laws of logs, is there a law that I can use to help me with this question? Okay, so bringing the exponent as a coefficient, which I can do on this side. What do I have right here? How would I read this? 2
Times 3 to the power of
times 3 to the power. So if I'm multiplying, what operation am I finding? What's another word for multiplying? find two numbers, I'm finding the what of two numbers?
Product.
The product. So I can use my product law. My product law says split these up by taking the sum of each. How does that help me? How is that going to move me forward to finding the answer for x? I can now bring the exponent down. I could not bring the exponent down before because I had this 2 attached to it. So I had to split it up. So now I have log 2 plus x minus 2 times log 3 equals x log 7. Now what would I do? Get rid of the brackets. So when I get rid of the brackets, what would I have? And? Okay, keep in mind, what's my goal?
Figure out x.
To figure out x. So in order to do that, what do I need to do?
Move the x sign to one side.
Okay? So to move it, I'm going to subtract it. So I'm going to be left with log 2 minus 2 log 3 equals x log 7 minus x log 3. Okay, now what would I do?
Factor out an x on the side of the x.
Okay? Then what would you do?
And then divide by log 7 minus log 3.
Right. I'm going to write mine as x equals, just because I'm running out of room, but it still would end up being the same thing. Do I have this in the form that the question asks for? No, because it wants it as a single log over a single log. So how do I make this part in here a single log?
Use the quotient law.
Use the quotient law. And what about this 2 that's out in front? Where is it going to go?
Oh, it goes to the power of 3.
Back to the exponent, okay? So I'm going to get log 2 divided by 3 squared. We're going to combine steps. And what will I get on the bottom?
Log 7 divided by 3.
So then my final part would be log 2 divided by 9 over log 7 divided by 3. And that's what I can put into the calculator to get my decimal answer. What did you get, Jessica?
Negative 1.775.
Is that what the rest of you got? Good. Okay, class example number 2 we get to skip because we already talked about it. We talked about if I have a simple exponential equation, convert it into logs and use my change of base. It's only for questions like C and D where you have exponents on both sides or you have a product, something being multiplied by the exponent, that I want to take the log first. Stats Canada says in the 21st century, Canada's population has been growing at an average rate of 1%. So I can use this exponential equation, P equals P of 0 times 1.01 to the power of n. P is the population n years after a known population, which we call P of 0. So if I know the population today, I can use this formula to predict the population 10 years from now. And this is a very important piece of information that the government wants to know. Grande Prairie wants to know that because that's how Grande Prairie decides their infrastructure. Knowing this information is how Grande Prairie's managed to build 2 Catholic schools in the next 2 years, on top of all of the other schools that are being built, because they've shown an increase in their population. So if the Canadian population at the beginning of 2001 was approximately 30 million, estimate in which year the population will reach 50 million, assuming that the average rate of growth does not change.
I kicked your camera by accident. I fixed it though.
You fixed it?
Yeah.
It's okay, I never watched the videos afterwards, so. So if I start off with P, with my formula, what would my variables be? So in other words, do I know the initial population? What I'm starting out with?
30 million.
30 million. So that's P of 0. Will it be necessary for me to write in all of the zeros? Well, let's check. What is my final population that I'm looking for? 50 million. Oops, one extra zero there. Is this a simple exponent or a more complex exponent?
Simple one.
Why is it simple?
Because there's only like the exponent on one side.
There's only one exponent. So if I go to solve this, what should my first step be?
Divide 50 million by 30 million.
So here's the question. Did I need all those extra zeros? Or could I have gone 50 and 30? I probably could have just done the 50 and the 30. Still works. 50 million divided by 30 million gives me what does it give you, Hannah? 1.6 repeating, which as a fraction is 5/3. So now that I have this simple exponent, how can I solve for n? So what did we do in A and B?
Oh, made each side a log, didn't we? Wait.
I could write it as a log. Log base 1.01 of 5 equals n. So then how do I put this in the calculator? Log 5/3 divided by log 1.01. Which gives me what did you get, Evan? 337. What does this represent? 51.337 what? years. So in what year, assuming that in 2001, what year is the population going to hit 50 million?
2053, maybe? Because wouldn't you have to round that up?
Okay, so it's a little bit trickier because how many days do I have in a year? I have 365 days. So does the population go from 40 million to 42 million like that? Or does it happen gradually over the course of a year?
Okay.
So if I take the 2001 and I add in my 51.33 years, what I get is 2052.33, which says estimate in which year. So it'll be sometime during 2052 that the population will hit 50 million. Not at the beginning of the year, but sometime during the year. Okay, two more things. The next question just looks at natural logs. We can solve these equations if we have a natural log. We're not just limited to common logs. You know you have a natural log if you have e. If you see the constant e, that means you have to use a natural log. So if I have the equation 7e to the power of negative 2x plus 9 equals 12, how would I solve this? What would I want to do first?
Subtract 9 on both sides.
Subtract 9 on both sides. Okay? Then what would I do? Can I separate the 7 from the e to the power of negative 2x? How would I separate it?
7 times e to the power of
So it's 7 times. So then how do I get rid of the 7?
divide by 7.
Divide by 7. So e to the power of negative 2x becomes 3/7. Now at this point, because I'm dealing with e, I'm going to take the natural log of each side. So I'm going to have natural log of e to the power of negative 2x equals the natural log of 3/7. All of the laws, all of the logarithm laws work for the natural log laws. So if I have an exponent, I can bring it out in front. The only thing that changes is this right here. The natural log of e is like taking the log of 10. What's the log of 10? 1. And the natural log of e is also equal to 1. And you can check that on your calculator. So now I have negative 2x equals the natural log of 3/7. So to get x by itself, what do I do?
Divide by negative 2.
Divide by negative 2. So dividing by negative 2 is the same as multiplying by,
1
pardon?
negative 1/2.
Negative 1/2. So negative 1/2 log 3/7. Or log 3/7 divided by negative 2. That's the exact answer. How would I write that to 3 decimal places? What did you get, Rachel?
0.424.
Yeah. So this is solving by algebra, an algebraic means of solving. We can solve graphically. To solve graphically, we use the same methods that we've used in prior math courses. We can either find the intersection, which means I need 2 graphs, I need a y1 and a y2, or I can find the zero, where I have one graph and I find where it crosses the x-axis, the zeros. This only works, or it's only useful, if all I need is a decimal approximation. So if the question says find the exact value, you have to use the algebra. If the question says determine the value to 2 decimal places, or to the nearest tenth, or to the nearest hundredth, you could do this graphically. And if it's a multiple choice question, you could do this graphically and then convert all of your answers into decimal approximations and see which matches. So if I have 4x to the power of 7, it's a question that we've already solved. If I wanted to use the intersection method, I would let y1 equal 4 to the power of x, and I would let y2 equal 7. So I'm going to give you a moment, and I want you to determine what the solution would be. So I would get an equation where I would have this straight line going through 7. And then I would have my graph of 4 to the power of x. And then I have this intersection point. What is the intersection point?
1.4036775.
So to the nearest tenth would be
1.4.
1.4. So x equals 1.4. How would I use the zero method?
If you move the 7 to the other side, so 4 to the power of x minus 7 in y1.
So I'd let y1 equal 4x minus 7. And I would get an equation, or sorry, a graph that would look something like this. And then what would I be trying to find on with my calculator?
The x-intercept.
The x-intercept, which on my calculator is what function?
0.
The 0. And I would still get 1.4. So the questions I have for you, question number 2 and then question 3A.